We have segment AB here in the first quadrant. PQ is the set of all segments in the first quadrant that have length 1. And if there's a point D on this segment AB, it may also be on the segment PQ. But there's one point C that is on AB, but is not on any of these other segments PQ. Since C and D are both on our segment AB, let's find an equation for this line that passes through points A and B. We'll find the slope between A and B, and then find the point slope form. Since D is on this segment, if it has x-coordinate lowercase b, then the y-coordinate is negative b root 3 plus root 3 over 2. D is also on this segment PQ, so let's find the slope between D and P. And we'll say that our point P has an x-coordinate of A. We'll use this for our y-coordinate, and this is over the change in x. So the line that passes through D and P has this equation, and we'll expand this. When x is equal to 0, we'll get the y-coordinate of this point Q on the y-axis. So this is our expression for the y-coordinate of the point Q. We'll use the fact that the line segment PQ has a length of 1, and we'll substitute these distances into the Pythagorean theorem. The distance from O to P is A, and we'll square the y-coordinate of Q, and this sum is equal to 1. First, I'll FOIL out this numerator. We'll multiply by this denominator and expand it, and I'll distribute this A squared, and I'll subtract these three terms, setting all this equal to 0. We'll combine these two pairs of like terms. Now I'll multiply by 4 to get rid of this fraction, and I'll factor A squared from these three terms. Recall that this is true for all of those segments in the first quadrant that have a length of 1, including AB. Since AB is a solution, then our point A, which had an x-coordinate of 1/2, also solves this equation, so we can factor A minus 1/2 from the above equation. Multiplying by 2, we can factor out 2A minus 1. I'm going to use the regular long division algorithm to find the quotient, and I'm going to write my terms in decreasing powers of A. To match this first term, 4A to the 4th, I'm going to multiply my divisor by 2A cubed. Multiplying by 2A minus 1, I get 4A to the 4th minus 2A cubed. According to this algorithm, we subtract the black terms from the green terms above it. Subtracting, we lose these 4A to the 4ths, and our coefficient of A cubed is 2 minus 8B. We'll bring down this next term. To match 2 minus 8B, we'll multiply our divisor with 1 minus 4B times A squared, multiplying by minus 1, and we're going to subtract. So our coefficient of A squared is 16B squared minus 16B, and we'll bring down the next term. So I'll need to multiply by 8B squared minus 8B times A to get this same first term, and then I subtract 8B squared minus 8B times A. Subtracting the second line from the first, we're left with 8B squared times A, and then we'll bring down this last term, and we'll multiply by 4B squared to match this coefficient, and happily we get a remainder of 0. So 2A minus 1 does in fact divide our polynomial here in green. So we can rewrite this in this factored form, factoring out 2A minus 1, and our other factor is the quotient. Our first factor gives us the solution from our segment AB. Our second factor is a cubic, so we should have 3 more solutions here. Let's see if we can eliminate some of them. We're looking for a point on this segment AB where the distance between the x and y intercepts of segments that pass through C have a length of 1. So one such AB might look something like this, with A1 over here and B1 over here, and this distance is equal to 1. This is not valid because we need to have our x-intercept be positive. We have a second line that might look something like this, where A2 is our x-intercept and B2 is our y-intercept. These two can also have a distance of 1, but like our first example, these are not valid solutions. So these we can discard. So there is a fourth remaining distinct solution. It must not exist for this point C. This means our fourth root is a double root with A equals 1/2. If A equals 1/2 is another solution, we can factor 2A minus 1 from our quotient above one more time. So I'll copy this quotient down below, and we'll do our long division algorithm again. To match the 2A cubed, I'll multiply by A squared, and then we have minus A squared. We'll subtract the purple from the red, the 2A cubes disappear, and we'll drop this down, and we'll multiply our divisor by 1 minus 2B times A to give us 2 minus 4B A squared down here, and then we'll subtract subtract the second line from the one that came before it, and we're left with 8b squared minus 10b plus 1 times a. We'll drop down the 4b squared. Then in the quotient, we'll put 4b squared minus 5b plus a half, multiplying by 2a minus 1. We subtract once more, and we're left with this remainder. In order to have the double root, when we divide by 2a minus 1, we must have the remainder equal to 0. So we'll set this expression equal to 0, multiply by 2, and we can factor this and solve for b. We need to eliminate one of these solutions, so let's remind ourselves of what b is. B was the x-coordinate of our point D. When b is equal to a half, that's going to have the same x-coordinate as a, which means that our point D coincides with point A, and we can't have that, so we can eliminate d equals a half. Therefore, our solution is b equals 1/8. Since c is on our segment AB, it's going to have these x and y coordinates that look like this, so we'll plug in for b equals 1/8. The problem asks for the square of the distance from the origin to point C. This is 28 over 64, or 7 over 16. Simplified as a fraction in lowest terms as p over q, the problem asks for the sum of p and q, and our answer is 23. If you'd like me to solve any other math contest problems, please leave them in the comments.